Welcome to the Storing and Organizing Data module. This introduction section describes the content of the module. This module defines the storage types that are found in a modern data architecture. You'll learn to distinguish between the storage types and select the option that matches the requirements and constraints of your use case. And finally, you'll learn about secure storage practices for cloud-based data. The objectives of this module are presented across 6 sections, each with its own video. The module wraps up with a sample exam question. This section provides an overview of storage concepts and how storage is used to support a modern data architecture. Storage in the iterative data pipeline is far from a linear process. When data is ingested into the pipeline, it's placed in storage. The data can then be removed from storage, processed, and returned to storage for later use or to await additional processing and transformation. This in and out cycle of data illustrates that storage is key to your data pipeline. Your planning efforts should focus on how storage will be used to support your pipeline goals. In this module, you learn how to select the appropriate storage for your needs and how data is stored and organized to support your data analytics and machine learning pipelines. In the Design Principles and Patterns for Data Pipelines module, you learned about the AWS modern data architecture, including the tools and services that you plan to use to manage and govern your resources. In the diagram on this slide, note that storage is at the center. It's the core of this architecture. In the AWS Cloud, Amazon Simple Storage Service, or Amazon S3, provides you with object storage that is central to your needs. And Amazon Redshift provides the data warehouse. Other data stores include relational databases such as Amazon Aurora and non-relational databases such as Amazon DynamoDB. A modern data architecture enables you to empower individuals or groups to run analytics and ML workloads by using their preferred tools or techniques. There are cloud storage services for each of the 3 general types of file storage: block, file, and object storage. Each type of storage has its own advantages and use cases. Object storage can be used to store unstructured, semi-structured, and structured data, and Amazon S3 provides object storage. The service is highly scalable and has near unlimited storage capability. Each object in Amazon S3 is assigned a key, which is a unique identifier. When the key is paired with metadata that is attached to the objects, other AWS services can use the information to work with the objects. Thanks to economies of scale, cloud object storage comes at a lower cost than traditional storage. The data storage layer of the modern data architecture uses Amazon S3 and Amazon Redshift to provide unified, natively integrated storage. Amazon S3 provides the foundation of your data lake architecture. You can store, access, and query data from many data sources. You can then use this data immediately or place it in a low-cost, long-term storage tier such as Amazon S3 Glacier for later use. Amazon Redshift uses SQL to analyze structured and semi-structured data across data warehouses, operational databases, and data lakes. Because the service is integrated with other AWS services, including databases and ML services, Amazon Redshift can help you handle complete analytics workflows. The catalog sublayer stores metadata about datasets that are hosted in the storage layer. This metadata supports the ability to find and query data stored in the data lake and the data warehouse. AWS Lake Formation and AWS Glue work together to collect and store metadata and make it available when needed. The catalog makes it easier for consumers to search for and explore the available data. Take a moment to review the differences between data lakes and data warehouses. They are complementary storage types, with data warehouses drawing much of their data from the vast data repositories that are found in data lakes. The key difference lies in the data quality characteristics. A data warehouse stores highly curated data, whereas the data lake can have raw, untransformed, or uncurated data. This section discusses the storage types that are available for large sets of data, the type of data that they store, and the AWS services that are available for each type. Unlike with the data warehouse, you can store data as is in a data lake. It isn't necessary to structure the data before you begin to run analytics. Data lakes can store both relational data, such as data from a line of business application, and non-relational data from sources such as mobile apps, Internet of Things or IoT devices, and social media. You can store data without a particular focus on design or usage plans because the structure of the data or schema is not defined when the data is captured. Data lakes in AWS provide you with secure, scalable, and durable storage. After you migrate your data into an S3 data lake, you can employ purpose-built analytic services, such as Amazon Athena and Amazon EMR. You can run ML jobs and transform and query data in place. Additionally, data lakes in AWS can take advantage of Amazon S3 storage classes, which are purpose-built to provide the lowest cost storage for different access patterns. With Amazon S3, you can read and write data at the object level and use in-place queries. You can use Amazon S3 storage classes to store your data based on the data access, resiliency, and cost requirements of your workloads. The storage classes are designed to provide you with the lowest storage cost based on the access patterns you need to support. Amazon S3 also supports multi-part upload. This is a feature that you can use to upload very large objects. The student guide for this slide includes additional information about this feature. By using Amazon S3 storage classes, you can choose how to store data based on access needs and cost considerations. Analytics and ML workloads require large quantities of data, and you want to ensure that you store that data in the most cost-effective manner possible. The storage classes include S3 intelligent tiering for automatic cost savings for data with unknown or changing access patterns, and S3 standard for frequently accessed data. S3 standard infrequent access and S3 one-zone infrequent access are available for less frequently accessed data. S3 Glacier instant retrieval is available to archive data that needs immediate access. And S3 Glacier flexible retrieval is available for rarely accessed long-term data that doesn't require immediate access. For long-term archive and digital preservation with retrieval in hours at the lowest cost storage in the cloud, use S3 Glacier Deep Archive. If you have data residency requirements that can't be met by an existing AWS region, you can use the S3 Outpost storage class to store your S3 data on premises. Amazon S3 also offers capabilities to manage your data throughout its lifecycle. For example, you can set a lifecycle policy to automatically transfer data to a different storage class without any changes to your application. For more information about Amazon S3 storage classes, see the resources for this module in the Content Resources page of your course. This slide shows an example architecture for a data lake and the services that are common in it. This example uses AWS Lambda functions as its microservices, Amazon OpenSearch service for search capabilities, Amazon Cognito for user authentication, AWS Glue for data transformation, and Amazon Athena for data analysis. If you'd like to explore this data lake architecture more fully, the code to configure this example is available for download on GitHub. A link is available in the Content Resources page of your course. Lake Formation is a fully managed service that simplifies the process to build, secure, and manage data lakes by automating many of the complex manual steps that are required. Lake Formation provides a centrally defined permissions model, which augments your AWS Identity and Access Management, or IAM, permissions model. These permissions are enforced using granular controls at the column, row, and cell levels across AWS Analytics and ML services. With Lake Formation, you can identify your existing relational and non-relational databases or S3 data stores. You can also import them new. Lake Formation can then crawl and read your data sources to catalog and label the data within it, enabling users to find what they need in a more efficient manner. You can use Lake Formation to transform data to ensure consistency for analytics use, and you can use the Find Matches ML transform to clean and deduplicate data. Finally, Lake Formation provides storage optimization for governed tables through capabilities such as data compaction and garbage collection. Governed tables are metadata tables that are unique to Lake Formation. Governed tables are enabled through new APIs and support the 4 key properties of transactions, ensuring that they are atomic, consistent, isolated and durable, or ACID. This capability enables multiple users to concurrently insert and delete data across tables. Other users can simultaneously run analytical queries and ML models on those same datasets, all while returning consistent, up-to-date results. Here are a few key points to summarize this section. Data Lake stores unstructured, semi-structured, and structured data in object storage. You don't need to structure the data before you begin to run analytics. Amazon S3 promotes data integrity through strong data consistency and multi-part uploads. These features ensure that data that is retrieved from storage isn't partial or corrupted, and that large files can be uploaded in parts without corruption. AWS Lake Formation allows you to use governed tables to enable concurrent data inserts and edits across tables. This allows users to update datasets while other users simultaneously run analytical queries and ML models on those same datasets, all while returning consistent, up-to-date results. This section discusses the data warehouse storage concept with a focus on Amazon Redshifts data warehouse service. Data warehouses are centralized data repositories. The data contained within the data warehouses can be processed and analyzed to make more informed decisions. Structured and semi-structured data from sources such as transactional systems and relational databases flow into the data warehouse in a regular cadence. Data warehouses consist of 3 tiers. At the top is a front-end client, which presents your results through reporting, analysis, and data mining tools. The middle tier is made up of an analytics engine, which is used to access and analyze the data. The third tier consists of the database server, where your data is loaded and stored. This data is stored in one of 2 ways: in fast storage, such as solid-state drives or SSDs, if it is frequently accessed, or in low-cost object storage, such as Amazon S3, if it is infrequently accessed. Data can be automatically shifted between the 2 storage types based on how frequently it is accessed. A data warehouse can contain multiple databases of structured and semi-structured data. When data is ingested into the data warehouse, it can be stored in tables, each of which can be organized inside of schemas. Query tools use these schemas to determine which data tables need to be accessed and analyzed. Amazon Redshift is a fully managed petabyte-scale data warehouse service. The service consists of collections of computing resources called nodes. Nodes are organized into clusters that run an Amazon Redshift engine and contain one or more column-oriented databases. Each cluster has a leader node and one or more compute nodes. The leader node receives queries from client applications and then parses the queries and develops query execution plans. The leader node then coordinates the parallel processing of the query plans with the compute nodes and aggregates the intermediate results. Finally, the results are returned to the client applications. Amazon Redshift has multiple node types for you to choose from, so you can select the best node type to fit your specific requirement. Dense compute, or DC2 nodes, are designed for demanding data warehousing workloads that require low latency and high throughput. With DC2 nodes, you can have compute-intensive data warehouses with local SSD storage included. DC2 nodes are often used when the amount of data in your workload is less than 500 gigabyte. You can use RA3 nodes to optimize your data warehouse by scaling and paying for compute and managed storage independently. By choosing the number of nodes based on performance requirements, you pay only for the managed storage that you use. Therefore, you can size your RA3 cluster based on the amount of data that's processed daily. By using dense storage, or DS2 nodes, you can create large data warehouses by using low-cost hard disk drives, or HDDs. AWS recommends that you upgrade DS2 nodes to RA3 nodes to get more storage and improve performance for the same cost. DS2 nodes are often used when the amount of data in your workload exceeds 500 gigabytes. This diagram represents the elements of a data warehouse architecture in Amazon Redshift. The client applications are business intelligence or BI reporting, data mining, and analytics tools. The data warehouse cluster consists of 2 compute nodes and a leader node. Note that if a cluster is provisioned with 2 or more compute nodes, it will require a leader node to coordinate the compute nodes and handle external communication. When a leader node is present, the client applications only recognize the presence of the leader node and not that of the compute nodes. As mentioned, the leader node coordinates the compute nodes within the cluster and communicates with the client applications. With the exception of direct queries to reference tables that are stored on the compute nodes, the leader node will run all queries. Certain SQL queries, such as the current schema function, can only be run on the leader node. If such queries are run against a compute node, an error will indicate that the function isn't supported. While the leader node is responsible for compiling code for the elements of the execution plan, the compute node is responsible for running the code. The compute node returns the intermediate results of the query back to the leader node for aggregation. Each compute node has dedicated CPU, memory, and attached disk storage based on node type, and each node is partitioned into node slices. These node slices are allocated a portion of the compute node's memory and disk space. The node slices work in parallel to complete operations that the leader node assigned to the compute node. Using Amazon Redshift Spectrum, you can conduct fast, in-place querying against data that is stored in data lakes on Amazon S3. You can make Redshift Spectrum queries on a wide variety of data lake assets, including comma-separated value, tab-separated value, Parquet, sequence, and RCF file formatted data. With Redshift Spectrum, you can write SQL queries that combine data from the data lake and the data warehouse. When a user makes a query request that includes data from the data lake, Redshift Spectrum gets schema information from the lake formation catalog and uses it to query the data lake. Here are a few key points to summarize this section. Data warehouses are centralized repositories that consist of 3 tiers and can store structured data. Data that is ingested into the data warehouse is organized into tables and columns. Amazon Redshift is a fully managed data warehouse service provided by AWS. It uses compute resources called nodes to provide parallel query processing for rapid results. Amazon Redshift Spectrum is a feature of Amazon Redshift that can be used to conduct fast, in-place querying against data that is stored in data lakes on Amazon S3. SQL queries can be run that combine data from both your data lake and your data warehouse. This section discusses the importance of purpose-built databases, how they support data analytics and machine learning, and the considerations necessary for selecting your database solution. Choosing the right purpose-built database is key when selecting the application architecture that will support your analytics or ML workload. The database service that you choose will affect the volume and variety of what your application can handle and determine what type of data is stored and the format it's stored in. Your database selection also determines whether your application can handle the volume and velocity of data sets, as well as corresponding customer demand. Finally, your database selection will determine the operations that you're responsible for. Consider several factors when you select your purpose-built database. Application workload, data shape, performance requirements, and operations burden. Let's inspect these database selection factors to gain a better understanding of what each entails. First, consider the workload of your application. Will your database support e-commerce or content management, or will it strictly be used for analytical purposes? Next, determine the shape of the data that your application will be working with. Consider whether you expect your database to grow considerably over time and how the data is accessed and updated. After data shape, consider the performance requirements of your application. This is where you'll focus on the customer experience in terms of access and application performance. Finally, you'll need to consider the operations burden of your database, focusing on the support you'll need to provide to your database throughout the application's lifecycle. The student guide for this slide includes additional information about these factors. Let's take a moment to look at some common database use cases and the AWS services that are available to support each of them. We'll start with the most common database type, relational databases. Relational databases are commonly used in traditional applications, enterprise resource planning, customer relationship management, and e-commerce. In addition to using Amazon Redshift as their data warehouse, organizations use services such as Aurora, an Amazon Relational Database Service, or Amazon RDS, to streamline their customer experience. High-traffic web applications, e-commerce systems, and gaming applications can all be supported by a key-value database service such as DynamoDB. DynamoDB is a fully managed, non-relational database that provides fast, consistent performance at any scale. High-scale applications and serverless applications are two categories of applications that DynamoDB often supports. Content management, catalogs, user profile management, and web and mobile applications depend on document databases. Amazon DocumentDB with MongoDB compatibility is a fast, reliable, and fully managed non-relational document database. Graph database services such as Amazon Neptune can support fraud detection, social networking, knowledge graphs, and recommendation engines with your application. These use cases are all examples of highly connected data with rich relationship variety. When using AWS purpose-built databases, most of the operations burden is handled for you. By using fully managed databases, you can focus on developing features and innovating for your users. Here are a few key points to summarize this section. Your choice of database will affect what your application can handle, how it will perform, and the operations that you're responsible for. When choosing your database, consider the application workload, the data shape, performance requirements, and operations burden. This section discusses how storage is used as part of your data pipeline. This diagram represents what you've previously learned about extract, transform, and load, or ETL, and extract, load, and transform, ELT pipelines. Recall that with the traditional ETL pipeline, data is extracted from its source, transformed into a structured format. The structured format is ready to be used in analytics applications. This transformed data is loaded into structured storage, such as a data warehouse, where data scientists or analysts can query it. Note that the data is generally transformed while cached in memory, meaning that the transformation is completed before it is stored in a data warehouse. The trend toward bulk collection of unstructured and semi-structured data is shifting the paradigm from the traditional ETL pipeline to the ELT format. Data is extracted from its source and cleaned just enough to be stored in object storage, such as a data lake built on Amazon S3. Then, whichever data transformation engine is built into the data warehouse for relational and SQL workloads access the data. This pattern is powerful because it uses the highly optimized and scalable data storage and compute power of massively parallel processing, or MPP architecture. Let's take a look at some example architectures for both pipeline types in action. This slide provides a high level example of an ETL pipeline. In this example, the pipeline is an Amazon Kinesis data firehose stream using the data transformation mode with data destined for a Redshift cluster. Kinesis Data Firehose is an ETL service that captures, transforms, and delivers streaming data to data lakes, data stores, and analytics services. When the data transformation mode is enabled, as Kinesis Data Firehose ingests data, it's first buffered up to 3 megabytes. Kinesis Data Firehose invokes a specified Lambda function, which transforms the data and sends it back to Kinesis Data Firehose. This transformed data is sent to an intermediate S3 bucket, where it waits for Kinesis Data Firehose to issue a copy command to Amazon Redshift, which then loads data from the intermediate bucket into the Redshift cluster. The transformed data must contain the record ID, result, and data parameters in order to be returned from Lambda to Kinesis Data Firehose. Otherwise, records are treated as data transformation failures and can be sent to the optional backup S3 bucket. These records will contain useful metadata that you can use to troubleshoot and avoid future data transformation failures.